Dear all, so that in some of the videos you are not able to see the graphs which I plotted there. So this video I'm creating for all the graphs, and I'll explain the graphs one by one. So suppose for the first one, the resonance frequency one. So if I run this, so we will have this plot appearing there. So if you see that, the thing which I was explaining there is that you have this log space, log 10, starting from basically 10 raised to the power minus 5 and going up to 10 raised to the power 5 and with the size 1000. It means that you start from 10 raised to the power minus 5 and you go up to 10 raised to the power 5 and with a step size of 1000. Means this is your step size from this point to this point. And the another thing is that if you remove this grid on from here, then and you plot it again, then what will happen is that you will not be able to see the lines which were there earlier. So that's the use of grid on here. So you put it there, you run it again, then you will be able to see the lines there. Okay, so this is the explanation of the graph with respect to the program 1. You must know that this is your minimum frequency component, this is your maximum frequency component, this is your bandwidth, and these formulas all were derived in the theory. Okay, the second program was of filter. Let me close this figure first. So if I run it, so in the plot, I was explaining with respect to the first thing is that if I just comment this part, I comment it and I write plot y in the program, then you will see that you have the signal X with noise and another signal which is with the help of filter we are removing the noise. Now here you can see that these signals are out of phase, means they are not in same phase. So in order for these signals to be in same phase, we use this command which is filt, and then upload again, and you will see that we have now the signal with noise and without noise, they are in same phase. This is basically the use of this filt command here. It provides the filter action with making sure that they are in the same phase. Now the third program is your amplitude modulation, and with respect to it, if I run it, then we have this modulating signal and then the input signal, and then we have modulated signal. It should be modulated signal, not modulating signal. So you run it again and you will see this. So the red color is used to differentiate the modulated signal. So and this is your input xt. Okay, so this is your modulating signal frequency f equals to 1, fc equals to 50 is your carrier frequency, and 200 is your sampling frequency by which you are modulating your amplitude modulated signal. So it's use this command modulate x, means the signal with your carrier frequency with your fs. Okay, your basically modulating frequency is already here in terms of x, because x equals to sine 2 pi ft. Here we are using the amplitude of the signal equals to 1. Okay, and this is the plot. The third one is your amplitude modulated signal, where you have different so different modulating index. So depending upon your modulating index, you can have a variation in your amplitude modulated wave. These all are also derived in your theory class. This is the formula which we use there. I ask you to use this, trying using this function without dot. So I don't know whether you tried it or not, but I can show you something. So if I say my x is equals to 1, 2, and 3, and my y equals to, let's say, 2, 4, and 5. So if I use command x dot y, so then it will not index anything. If I use x dot y, it's again not letting me multiply it, but if I do use x dot star y, then I'll get the answer like this. So basically what's the use of this dot and star command together is that all the components of a matrix, means the first one will be multiplied to the first one of the second matrix, second of the first one will be multiplied to second of second matrix. In this way these elements are multiplied. But if I take another example where you have x 1, 2, and 3, 4, and you have y equals to 2, 3, 4, 5, and now I use these commands again, x star y, then we have this answer. And when I use this command as x dot star y, then I have this answer. So what's happening here is that when you are using x star y, the normal matrix multiplication is happening, means the first row is getting multiplied to the first column of y. So it's 1 into 2 plus 2 into 4. So it's 10. In a similar way, these will be multiplied. And when you are doing this, then the first element of this will be multiplied to this. Second element of this will be multiplied to this. And you'll get the answer. So that's the difference between using a dot and a star. So here, every time instant, because we have different times. So whatever the time instant this one has, the same time instant I want to multiply with the time instant of carrier signal. So in order to make sure that the both times are same, we use this dot and star command here. Okay. Next, the graph, you can see that with respect to graph, how the modulation is happening. So the amplitude modulation, depending upon the value of your amplitude, the amplitude is increasing. And then when the negative cycle comes, you can see the amplitude is falling and decreasing depending upon the variation in the modulating signal. Whose amplitude is changing? The carrier signal amplitude is changing. And with respect to your modulating signal, if you change the value of, you can see that the variation here is 11.5 and 10.5. That is the maximum variation. The carrier originally was 10 and minus 10. Modulating signal was plus 5 and minus 5. Now if I change my modulation value by, let's say, 9, and I run it again, then you can see that the variation here. And this, so it's getting changed. It becomes, sorry, I think I changed it the wrong place. No, it's right. So this is the same that now if I make my modulation index to let's say 0.3, then you will see that it is becoming 18 and 17.5. Remember, for AM, the modulation index, basically, the higher is the value of modulation index, the lesser will be the amplitude of the signal you are getting after modulation. And for your frequency modulation, if you are increasing the value of beta, or let's say modulation index, then you will see the variation in your frequency depending upon that. So frequency will increase at certain point and it will decrease. And here the amplitude is changing with respect to it. Now, the last one is this of frequency modulation. If I run it, so two part of it is run, run. And it is asking me to provide the modulation index. So I provide 15. Sorry, I cancel the first one. So I run it. Now I provide 15 here. And then we'll see it again. So you can see that with respect to graph, when this signal is positive, you have higher frequencies. When you have on the negative side, it has lower frequencies. Again, higher, more frequencies, positive, negative, less frequency components. And this is your demodulated wave. This is the signal which we transmitted, and this is the signal which we are getting after demodulation. Depending upon the your quality of your filter, the stages of filter you are using, you can get it as close as possible to this one. Okay. This is all for the details with respect to your graphs.